Okay, so since we are needing a little more lecture time in physics, I'm going to go ahead and record this. So this is about vectors, which applies to stuff we're doing in Chapter 3. We're not getting super heavy into vectors, but I wanted to spend the time to talk about vectors. So what we've dealt with mostly up to this point in life are scalars. And scalars are quantities that um, have magnitude, but they don't have a direction. So, 40 pounds per psi, pounds per square inch, 25 degrees Fahrenheit. So pressure, temperature have values, but they don't have a direction to them. Now, in contrast, we have vectors, which are very important in engineering and physics. And vectors have both a magnitude and a direction. So here we had pressure. We said that was an example of a scalar. Temperature, another scalar. Vectors, position, velocity, acceleration. So those are the three. I guess displacement as well. Those are the four that we've dealt with up to this point. Time is a scalar. So of those five quantities that we've been dealing with so far, well, initial velocity, final velocity, acceleration, and displacement, those are all vectors. Scalar time is the only scalar that we've dealt with so far. Another example, which we'll cover in the next chapter, chapter 4, is force. Then there's things like momentum. There is, what else is there? Well, actually up here, in terms of scalars, there's energy. Down here, there's torque. And then you can get into, well, electrical forces is just a different kind of force. Anyway, those are the ones. So a lot of stuff in physics is associated with vectors. And as I said, it has a magnitude and a direction. So typically we can deal with vectors in a visual sense, what's the right word? Picture sense. And we can deal with them in more of an analytical sense. So we're going to talk about both of those. So the first thing is that vectors in a graphical sense are represented by a line. And the length of the line is proportional to the magnitude. I don't say it's equal to the magnitude because things like force don't have length. Position has length. Displacement has length. But velocity, all these other ones don't have length. So the vector length is proportional to the magnitude. And so you're going to have some kind of a scale that you would have to relate the length somehow is going to be related to the magnitude somehow. So if we were drawing vectors, we might have a scale that said, this distance is equivalent to 1 Newton. So if we have twice the distance, it's 2 newtons. So the distance is representative of the magnitude. Then you've got the direction. So the direction we usually deal with, the directionalities are associated with the Cartesian coordinate system. So this is your typical XY thing that we're used to. So there's nothing new. You could also do it relative to maybe a polar coordinate system, some other system, but we're going to deal with Cartesian in 2 dimensions. You could also make it into a 3-dimensional problem as well. You could have 3-dimensional vectors. You could have 1-dimensional vectors. 1 dimension, basically, the direction is associated with the plus or minus. So you've got this coordinate system, x, y. So even going back to these different vectors, all of these are going to have an x and y and possibly z component. But the lengths inside this x, y coordinate system are going to be, the length of the vectors are not going to be associated with distance, but they're going to be associated with the magnitude of the quantity that we're interested in. So for example, let me just give you an example. So I've got a vector here. Let's say we're looking at velocity. So by drawing these vectors in space, we're saying that the velocity in space, in this xy coordinate plane, the velocity at this point is pointing with this directionality to it, and the length of the vector is proportional to the velocity. Likewise over here, you've got an x and y coordinate. So that's saying at this point in space that the velocity is going to be proportional to the length, and the direction is going to be indicative in the xy plane of this relative to some base arrangement. Okay, so that's because a lot of times you think of vectors as the length being distance, but the length is proportional using some kind of a scale to the magnitude, and where the vector is placed is depending upon where in the coordinate system you're located. Now it turns out that a lot of vectors are put in what we would call standard position. So here's a vector, has a certain length which is proportional to the magnitude. It's located at this point x, y, but a lot of times we'll just move the vector so that one point of the vector is located at the origin. So that kind of comes back to another terminology thing here. So this part here is called the tail, and this part with the arrow is called the tip. So the vector is pointing from the tip to the tail, and the tail is the tip is telling you which direction it's going. Because we could have the same looking scenario if I clone this thing, but what I do is if I flip the tip and the tail, so the start becomes this and the end becomes this. Now they look like they have the same direction, they're the same length, but this one is pointing down to the left and this one's pointing up to the right. So these vectors are not the same because of where the tip is relative to the tail. Okay, so we'll come back to that. So that's the tip, that's the tail, the tip. Why do they call it that way? It's like an arrow. So on an arrow you have feathers, which is the tail, the arrow, and the tip is where the point is that is shooting or whatever you're shooting at. Okay, so that's that terminology. Now let's move this thing back to standard location. So obviously the magnitude is easy, it's just the length of the arrow. Now in terms of the directionality is concerned, there are a couple of ways of doing this. One is the angle between the positive x-axis and the vector. And do we use degrees or radians? I'll tell you in a second. So this is the angle between positive x-axis direction and vector direction. And you kind of think of this as, when we did one-dimensional motion, we defined where x was equal to 0. So this is where the angle would be equal to 0, is the x-axis. So if this thing is pointing horizontally from left to right, the angle is 0. If it's pointing horizontally from right to left, it's going to be 180 degrees. So that answers the question. This is in degrees. Now, when we get to rotational motion, we'll make theta into radians. But when it comes to two-dimensional motion in Chapter 3, which is projectile motion, we show the angle is in degrees. So for right now, just think of angle in degrees. So if you have something pointing this way, let me get where's my line here? So this one would be 90 degrees, this one would be 180 degrees, this one would be 270 degrees, and this would be 0 degrees. So those are the kind of the main directions, and you've had geometry, so I'm not going to belabor that point. Okay, so that's the direction. So I could define a vector. I could say vector A. Okay, so I'm going to use vector A. So one way of doing vectors is a capital letter with an arrow pointing from left to right. It's always from left to right. It doesn't matter where the vector's actually pointing. For the notation, it's always pointing from left to right. And we could say vector A has a magnitude of 12 newtons. That's the unit of force, which we'll come to Chapter 4. And a direction of 46 degrees. Now, if I don't say, I could define it relative to some other coordinate axis, but ultimately my calculations are going to be based on using the angle between this vector and the positive x-axis. So this is about 45 degrees. So if I were to take another vector, let's call this vector A. Okay, so this is vector A. Let's just pick another vector. So let's call that vector B. And, relative to vector A, they're pretty close to each other. Maybe slightly smaller in length. The angle for vector B would be here. So it would be greater than 90. So let's do that. Let's just give it some values. So I'm going to say vector B has a magnitude of 11 newtons and a direction of let's say 104 degrees. So it's going to be between 90 and 180. Okay. And if it's in the third quadrant, the angle is going to be between 180 and 270. Fourth quadrant between 270 and 360. Now, could you have negative angles? Yeah, you could. You could either define, so let's put an angle in the fourth quadrant. Let's use blue. So now the angle is in the fourth quadrant. So could you have two angles? Could you have this angle here or this angle here? And the answer is yes. Okay, so I'm just going to do it both ways. We'll call this vector C. So vector C, this looks a little longer, so I'm going to say has a magnitude of 13 newtons and a direction okay, so the direction, so I'm going to, looks like, I'm going to say negative 50, so it could be two directions. So we could say it has a direction of negative 50 degrees, or you could say it's positive 310 degrees. These have to add up to 360, so 310 plus 50 is 360. Okay, so that's how you define the angle, the magnitude and direction. And I could, I could define angle B here, or vector B with respect to the positive y-axis, but then I'd have to convert it ultimately to being with respect to the positive x-axis. So ultimately, you got to do that. Okay, what am I going to talk about next? Now, so there's really two things you're going to do with vectors. You're going to take the information given as a magnitude and direction and break it up into components, or you're going to have the components and you're going to put them back into a magnitude and direction. So that's what we're going to do next. So let's put up another coordinate axis like this, and we'll pick something in the first quadrant, like here. Okay, so that's vector, and we'll call that vector A. And let's give it a magnitude. Okay, so here's another thing. The magnitude you show by these two vertical lines on either side. This is magnitude. So you can either say magnitude or you can write it out. So the magnitude of vector A, we'll say, is 35 meters per second. So we're dealing with a velocity vector. And we'll define theta here, and we'll say that the angle theta is 71 degrees. Okay, now in terms of components, what we would do is we would take this triangle or this vector and treat the vector as the hypotenuse of a right triangle. And one side of the right triangle goes in the x direction, and one side of the right triangle goes in the y direction. So we would call this part right here, this part of the right triangle, a sub x. That's the x component of the vector A. And then up here, the vertical is going to be the y component. So we use these subscripts. We use subscripts a lot in physics to represent like beginning and end, condition 1 and condition 2, x direction, y direction, z direction. Okay. So we can define this vector by its magnitude and direction, or we can define it by its components. And the components, because this is a right triangle, you just use simple right triangle geometry. So let's go over here. What do we know? We know that the sine of theta, the angle, is equal to the opposite over the hypotenuse. And in terms of lengths, this length, the length of the hypotenuse is the magnitude of A. So that's going to be the magnitude of vector A is the hypotenuse, and the opposite side is the y component of the vector. So when I talk about components don't have they have a direction, but the direction is indicated by the subscript. So I know this is pointing upward with a certain length. So that's the y component. The magnitude of the vector is the length of the vector. So if I solve for the y component of the vector, it's just equal to the magnitude of the vector times the sine of the angle theta. Now the x component is associated with the adjacent side. So the cosine of theta is equal to the adjacent over the hypotenuse, the adjacent being the x component and the hypotenuse being the magnitude of the vector. So if I solve for the component a sub x, it's going to be equal to the magnitude of vector A times the cosine of the angle theta relative to the x-axis, positive x-axis. So now we can just plug those in and see what we get. Okay, so a sub y is going to be equal to 35 meters per second. That's the magnitude of vector A times the sine of 71 degrees. So make sure your calculator's in degrees. which I'm not sure what it is. Mine's in radians, so I change degrees. So we take 35 times the sine of 71. And we'll get 30. I'm going to go ahead and carry one additional significant figure here, 33.1. We'll assume it's, and the units are meters per second because sine has no units. And likewise, you can do the x component. It's 35 meters per second times the cosine, 71 degrees. 35 times cosine of 71 is 11.4 meters per second. Okay, so those are the components of the vector A. Let's do another one in a different direction. So let's add a page. So let's put it in the fourth quadrant. So we're going to do this. Okay. Now I'm going to go ahead and define it relative to the positive x-axis going counterclockwise. So this is my angle theta. And so let's call this vector B. So the magnitude of vector B, we'll make it, what was the last one we did? 35. So let's do something different. 35. Where's my eraser? Oh, there we go. Okay. So let's say it's 52 meters per second. And theta is going to be 348 degrees. Okay, so we're going to break it up into two components. We're going to have the x component, which is going to be equal to the magnitude of vector B times the cosine of theta. And b sub y is going to be equal to the magnitude of b times the sine of theta. Let's see if it works out as far as what we expect. Because if you think about this, the components are going to be positive x, but it's going to have a negative y component because the y is going to be pointing downward. So hopefully this will just all turn out to be perfect. So let me leave a little room here. Okay, so the magnitude of B is 52 meters per second times the cosine of 348 degrees. 52 times cosine of 348 degrees is 50.1 meters per second. So that's positive, which makes sense. And down here we have 52 meters per second times the sine of 348 degrees, which is negative 10.8 meters per second, which makes sense. It's pointing negative. Okay, so that's how you go from magnitude and direction to the components. Now the magnitude and the components are quantities. They're scalars. The original vector is a vector because it's got a magnitude and a direction. So to represent this as a vector, you either have to say the magnitude is this and the vector direction is this, or you have to say the x component is this and the y component is that. They're equivalent to each other. Okay, let's go the other direction. It's a little harder going the other direction. What we'll do is we'll do one that's in the third quadrant. So let's say I gave you a vector that's going like this. Okay, and then what I'm going to do is I'm going to tell you what the components are. So b sub x would be negative 20.0 meters per second, and v sub y would be equal to negative 33 meters per second. So I'm giving you the components, and now you have to figure out what the magnitude and direction of this vector is. Well, we know the angle has to be in the third quadrant. So that's theta. It has to be somewhere between 180 and 270 degrees. So if I show the components of the vector, you're gonna have a negative x component and a negative y component. And this angle here is 90 degrees. We'll call this vector C. We don't know what the magnitude of C is. Actually, let's just call it vector C. So you've got C sub x, you've got C sub y. C sub x is negative, C sub y is negative. So you just have to go the other way. And we have to use, instead of using the definition of the sine and the cosine, we're going to use the definition of the tangent and the distance formula. So what we can say is that the magnitude of vector C is equal to the square root of C sub x squared plus C sub y squared. So it's the Pythagorean theorem. One side squared plus the other side squared equals the hypotenuse squared. And then just solve for it. And because the magnitude is always positive, we take the positive square root of this whole thing. So to find the magnitude of this vector, we just take the square root of the components. So you get negative 20 quantity squared plus C sub y, which is negative 33 meters per second, quantity squared. And because we're squaring it, we're going to get a positive quantity. So you got negative 20 squared plus negative 30 squared, and you get the square root of positive 1300 meters squared per second squared. And if we take the square root, we should get a number greater than the biggest of the two. So we get 36.1 meters per second. So that's the magnitude of vector C. So if I have the length of vector C sub x being 20, and the length of vector C sub y being 33, the length of the hypotenuse is just the length that represents the magnitude of the combined vector is 33.6. Now the angle is a little bit harder because what we can say is that theta, let's go back here. We can say that the tangent of theta equals C sub y over C sub x, the y component over the x component, because this angle, here we're dealing with a right triangle, but when we deal with this angle theta, we're dealing with angles of any value. If you go back to pre-calculus, that's why you're supposed to have taken pre-calculus before this class. So there are actually two solutions to this. There's the first quadrant solution and there's the third quadrant solution. Because you could either have positive C sub y and positive C sub x, or you could have negative C sub y or negative C sub x. So if I just take the inverse tangent, I'm not going to get the right answer. You have to do the whole reference angle thing. So what you look at is, you would say since, oh, why did I put B here? It should be C. C. Okay. So you would say since C sub x and C sub y are negative, the answer for theta is in the third quadrant. So what we'll do is we'll find the reference angle. So remember, the reference angle is equal to the inverse tangent of the absolute value of C sub y over C sub x. And that's going to put as a number in the first quadrant. So for our particular case, we have C sub y, which is negative 33 I'm going to go ahead and put the units on here. Negative 20. So the reference angle for this calculation, we're going to take the inverse tangent of negative 33 divided by negative 20, which is 58.8 degrees. Okay, so that's the reference angle. But if you remember back from pre-calculus, especially if you had me, we talked about reference angle a lot. So what we have is we need the third quadrant solution here, not the first quadrant solution. And that's what would happen if I just took the inverse tangent without the absolute value sign. It would give me 58.8 degrees, which is the first quadrant solution. But the third quadrant solution says that the angle is equal to 180 plus the reference angle. We'll write them all down here in a second, but for the third quadrant, that's the case. So my theta here is going to be 180 plus 58.8 degrees. So 180 plus 58.8 is 238.8 degrees. Okay, I added a little extra significant figure, so I probably should make that 239. Don't want to get too many significant figures. Okay, so 239 degrees. And you can see if I take the tangent of 239, I'll get a number, and if I take the tangent of 59, I'll get another number, and they'll be at the same number. So let's just plug that in our calculator and find out. This is 1.664, and the tangent of 59 degrees is the same thing, 1.664. So that's the only tricky part in going from components to magnitude and direction. The magnitude is a piece of cake. You don't have to worry about anything there. But when it comes to the direction, you've got to go back and look at the signs and figure out what quadrant you're in, and then make sure you're in the appropriate quadrant. Okay, so what have we done so far? We talked about, given the magnitude and direction, finding the components. We talked about, given the components, find the magnitude and direction of the vectors. Okay, next thing we're going to talk about is adding and subtracting vectors. Now, in the projectile motion section, we don't really need to add and subtract vectors. But when we talk about forces, we will need to add and subtract vectors. Now, actually, we could, there's something called relative motion. There you would need to add and subtract vectors, but we're not going to talk about that too much. We're just going to worry about doing projectile problems when it comes to two-dimensional motion right now. But we're going to introduce the idea of adding and subtracting vectors. So we're going to do the same thing. We're going to introduce the topic using graphical means, and then we're going to do it analytically. Okay, so let's do two vectors here. So we've got two vectors. We've got vector A. Now when you do things graphically, you don't have to break them up into components. So this is vector A, and then over here we've got vector B. So what does it mean to add vectors? Well, you don't just add the magnitudes and directions. What you have to do is you have to take the one vector first, which it doesn't matter. The order of vector addition is irrelevant, just like normal scalar addition. It doesn't make any difference. That's what you're used to, is scalar addition, just adding numbers together. So what you do is you take one of the vectors and you put it in standard position where the tail is at the origin and the tip is somewhere out in space. Then you take the second vector and you put the tip of the first vector connected to the tail of the second vector. And what we call the resultant vector goes from the tail of the first vector to the tip of the second vector. So this is the resultant vector. Sometimes we use R for resultance vector. So this is showing, saying the resultant vector is equal to the A vector plus the B vector. So this is how we're doing it symbolically in terms of vectors, just like you would normally do with scalars. Here we're doing it graphically, tip to tail, and then you go from the tip here, tail here to the tip there. Now I'm going to take these, I'm just going to switch them. So let's say we do B first. So we're going to put B in standard position, and then we're going to take vector A and put it over here. So it's the same thing. All I've done, the second case is the second case, all I've done is say vector B plus vector A, and you see I get the same resultant vector. So order of operation for addition and subtraction of vectors is irrelevant. And you can do more than, if you had 3 vectors. So let's put another vector here. Let's use black. So let's say this is vector C. Vector C, like that. Okay. So now if I added vector C, I have to get rid of this resultant vector because it's going to be different. Okay, so if I take vector C and I add it, again, the order is not going to make any difference. I guess I'm doing the second case. So I'm adding vector C here. So I'm going to do B, A, and then C. So what you would do is you take this and then connect it to there. So this would be B plus A plus C. And finally the resultant vector would be there. Now all of the original vectors were defined relative to the origin, but I can move them around in space. Actually, where the vector is in space doesn't matter. The only thing that matters is what is its direction and what is its magnitude. So vector A located here is the same as vector A located there. They're the same thing. So I can move these things around. And when you do vector addition graphically, you have to move them around to make that happen. So that's vector addition. Now let me get rid of C again. Let me get rid of resultant vector. Put these back here like they were originally. And let me make a copy of it. Okay, so let's clone that thing. And pull it over here. Okay, so we got the same 2 things. So actually, before we do subtraction, so let's say you have, let's define vector C differently this time. Let's define vector C as the negative. So vector C is equal to the negative of vector B. So here's vector B. What's the negative of vector B? Okay, so which we're going to call C. So I'm going to clone this thing. So it's got the same length. What I'm going to do is switch the tip and the tail again. So this is vector C. So you see it's the same length as vector B, but it's pointing the opposite direction. So I could put that here, and you can see it just forms a straight line. We'll call that vector C. Okay, so vector C is negative vector B. So if I wanted to do the operation A minus B, that would be the equivalent to vector A plus vector c, because c is negative b. So all you do for vector subtraction is you take the vector you're subtracting, switch the tip and the tail, and then you draw the resultant vector. So let me grab this vector c here, put it over there, move that over there, and if I draw a line from here to here, let me change the color. Change the color. Go down here, change it, make it purple. Okay. So this is this vector c vector. This is the resultant vector here. The resultant vector is a plus c, which is the same as a minus b. So a plus b would be up here, and a minus c would be down there. I mean, a minus b would be down here. So what we can say is we only ever, graphically, we add vectors together. Because trying to, and so to do it, you have to, subtraction of vectors has to be converted to addition by changing the direction of the subtracted vector (180 degrees). Now in forces we add vectors all the time. Where we have subtraction of vectors is when we get to deriving rotational motion. So there we're going to take one vector and subtract another vector to get the final answer of what we're trying to come up with. Okay, so that's addition and subtraction. To subtract, take the original vector that you're subtracting, have the same length, change the direction to the opposite direction, 180 degrees, and then add the first vector with the inverse, additive inverse, basically, of the second vector. Okay, so that's how you do it graphically. The order of operation doesn't make any difference. The length of the vectors are representative of the magnitude of the vector. Doesn't have anything to do with that it has to be a vector that has units of length. The last thing we're going to talk about is adding or subtracting vectors analytically. So add and subtract analytically. And the way we're going to do that is we're going to go back and use something we've already created. So back here we took vector A and we broke it up into two components. And we took vector B and we broke it into two components. So what we want to do is insert a page here and do this, use these two examples to do the addition and subtraction, or addition. So if we had vector A, that consisted of two components. Let's write those down. So you've got A sub x equals 33.1 meters per second, and A sub y is equal to 11.4 meters per second. We had vector B over here, which ended up being 50.1. So the x component was 50.1 meters per second, and the y component is negative 10.8. Okay, so when we do the vector addition, vector A plus vector B, the way we do that is you add x components and you add the y components. And the way we represent that is we say that the x component of the resultant vector is equal to the summation of the x components of the original two vectors, and the y component, the resultant vector, is the y components of the individual vectors. And that's why it's important to be able to go from magnitude and direction to components. So let's write these down here. So a sub x is 33.1 meters per second. B sub x is 50.1 meters per second. And down here, a sub y was plus 11.4 meters per second, and b sub y was negative 10.8 meters per second. So you just do the math. 33.1 plus 50.1. So that's 83.2 meters per second. And 11.4 minus 10.8 is 0.6 meters per second. So that gives me the components of the resultant vector. So then, finally, what you can do is you can say that the magnitude of the resultant vector is equal to the square root of the square of the x component, the resultant vector, and the y component, the resultant vector. So that's going to be 83.2 meters per second squared plus 0.6 meters per second quantity squared. It's going to be very close to 83.2 because the second number is so small. So you get 83.2 squared plus 0.6 squared, take the square root, so that's 83.2. I mean, it rounds off to being about the same thing, meters per second. And if you think about where this resultant vector is, it's very close to the x-axis because it's got a really small y component, but it is in the first quadrant. So because it's in the first quadrant, I can find the angle very easily. I don't have to think too hard about this, just the inverse tangent of the y component over the x component. So if we do that, inverse tangent of 0.6 divided by 83.2, which is 0.41 degrees. Okay, so really close to the x-axis. Now, if the x and y components were, any of them were negative, both negative, one negative, the other positive, you would have to use the reference angle and figure out which quadrant you're in. Which reminds me, I forgot to do this earlier. You know, the equations were for the three quadrants. In the first quadrant, the angle is equal to the reference angle. In the second quadrant, the angle is equal to 180 minus the reference angle. I'm doing this in degrees. Third quadrant is 180 plus the reference angle. And in the fourth quadrant, it's 360 minus the reference angle. So those are the formulas depending upon which quadrant you're in. So this one we were in the first quadrant, so we just, you know, here theoretically I guess we should have said the reference angle is the inverse tangent of the absolute value, and then you would say theta, because it's in the first quadrant, is just equal to the reference angle. So that's how you handle components, or how you handle vectors. If you're given the magnitude and direction of a vector, you have to break it up into the components, which are scalars. To add two vectors, you add the x components of the vector and the y components of the vector. That give you the x and y components of the resultant vector. And then to find the magnitude of the resultant vector, you use the Pythagorean theorem. It's always going to be positive. And then the angle, you have to use the inverse tangent, but again, making sure you look at the which quadrant you're in. So hopefully that helps some. We're probably going to do some assignments. I know I've got an assignment that basically does what we just did to make sure you know what you're doing. And I'll assign that later, but I think that's enough for right now.